Choosing the wrong messaging system today can silently damage your enterprise architecture tomorrow. You might not notice it in the first few months, but over time it shows up as scalability bottlenecks, unexpected latency, message loss, and operational nightmares that are extremely hard to undo. This is why the decision between Kafka and RabbitMQ is not just a technical choice, it's an architectural bet that can impact your system for years. Welcome to the Topictrick YouTube channel, where knowledge is inspiration. In this video, we're going to take a solution architect level deep dive into Kafka versus RabbitMQ, understand how they are fundamentally different, and help you decide which one is right for your enterprise architecture in 2026 and beyond. Modern enterprise systems are complex and highly distributed. They demand real-time data processing, seamless communication between microservices, and fault-tolerant message delivery. In this context, the messaging layer is no longer just infrastructure sitting quietly in the background. It becomes the nervous system of your entire architecture. When this layer is poorly chosen, the consequences are severe. Messages can get lost when traffic spikes, latency becomes unpredictable, operational complexity grows out of control, and the system struggles to scale as the business grows. When we look at the messaging landscape, two names dominate most enterprise discussions. Apache Kafka has become the backbone of streaming data platforms, processing trillions of messages every day across large global enterprises. RabbitMQ, on the other hand, is a trusted and battle-tested message broker that has been in production use since 2007, known for its reliability, flexible routing, and strong delivery guarantees. Both solve messaging problems, but they are built very differently, and that difference determines where each one fits best. At the heart of this comparison is a fundamental architectural distinction. Kafka is built as a distributed, immutable, append-only log. Every message is written to disk and retained for a configurable period of time. Consumers don't remove messages when they read them. Instead, each consumer keeps track of its own position, called an offset. This means the same data can be consumed multiple times by different consumers, or even replayed later. For example, an order-created event can be read by a billing service, an analytics pipeline, and a fraud detection system independently, all without interfering with each other. RabbitMQ follows a more traditional message broker model. Messages are published to exchanges, routed to queues, and then pushed to consumers. Once a consumer acknowledges a message, it is removed from the queue. The broker controls message delivery, not the consumer. This model is ideal when the goal is to make sure a task is delivered and processed exactly once. For instance, when you send a background job to resize an image or send an email, once the worker confirms completion, the message disappears. This architectural difference cascades into everything else, including performance, scalability, and operational complexity. Kafka log-based design enables event sourcing and large-scale stream processing. RabbitMQ's broker-based design enables sophisticated routing, reliable delivery, and well-defined messaging patterns. Kafka truly shines in high-throughput event streaming scenarios. One major use case is event sourcing and CQRS, where every state change in the system is stored as an immutable event. Instead of just storing the current state of an entity, you can replay the event log to reconstruct state at any point in time. For example, in a financial system, you can replay account events to understand exactly how a balance changed over time, which is invaluable for audits and compliance. Another area where Kafka dominates is real-time analytics. Kafka can ingest millions of events per second from sources like IoT devices, application logs, or transaction systems. These streams can then be processed in real time using Kafka Streams or other processing frameworks. With Kafka Connect, enterprises move data between databases and data lakes with minimal custom code. With proper tuning, Kafka handles over 1 million messages per second and scales linearly by adding more brokers and partitions. RabbitMQ, on the other hand, excels in scenarios where message routing and delivery semantics are more important than sheer throughput. It offers a rich set of exchange types, such as direct, topic, fanout, and header exchanges. This allows messages to be routed by keys, patterns, or complex rules. For example, you can route messages to different queues based on region, priority, or customer type without embedding any routing logic in your application code. RabbitMQ is also ideal for work queue patterns. Tasks can be distributed across a pool of workers, and each worker acknowledges the message only after successful processing. If a worker fails, the message is automatically requeued and retried. This makes it perfect for background processing jobs like video encoding, report generation, or order fulfillment. RabbitMQ also supports request response, or RPC-style communication, using correlation IDs and reply queues. This allows synchronous-style interactions between services when needed. One of RabbitMQ's biggest strengths is guaranteed delivery. Features like publisher confirms, consumer acknowledgements, and persistent messages ensure that data is not lost, even in the face of failures. This makes RabbitMQ a strong choice for financial systems or business workflows where every individual message matters. When we compare performance and scalability, the numbers highlight their design goals. Kafka is optimized for throughput. It can process around 1 million messages per second per broker, with batching and proper configuration. RabbitMQ typically handles around 50,000 messages per second per node for persistent queues with acknowledgements. In terms of latency, RabbitMQ often achieves very low end-to-end delivery, around 5 milliseconds, making it suitable for command-style messaging. Kafka's average latency is slightly higher, around 10 milliseconds. But remember, Kafka is optimized for sustained high throughput rather than ultra-low latency. Scalability also differs significantly. Kafka scales horizontally by adding brokers and increasing partition counts, and it can grow to hundreds of nodes in large deployments. RabbitMQ scales through clustering or federation, but queues generally live on individual nodes. In practice, RabbitMQ clusters usually scale to a few dozen nodes, as mirrored queues can impact performance. Fault tolerance follows the same pattern. Kafka uses replication and leader election to avoid data loss, while RabbitMQ relies on mirrored queues and failover. This offers stronger per-message guarantees, but with different trade-offs. Operational complexity is another critical factor. Kafka has a higher initial setup cost. It requires careful planning around partitions, replication, and operating system tuning. Day-to-day operations include monitoring consumer lag and understanding internal concepts like ISR and log segments. Put simply, Kafka demands a solid understanding of distributed systems. RabbitMQ is generally easier to get started with. Installation and clustering are straightforward, and it has a powerful, intuitive management UI. Day-to-day operations focus on monitoring queue depth, managing memory, and maintaining topology. While RabbitMQ is more approachable, keep in mind it can still become complex at scale. Beyond the core platforms, both ecosystems add significant value. Kafka offers Kafka streams for native processing and a schema registry that enables safe schema evolution. Together, these components turn Kafka into a full-fledged data streaming platform. RabbitMQ offers a rich plugin ecosystem and built-in support for enterprise patterns. This includes priority queues, dead letter exchanges, and message TTLs. So, how do you decide? Kafka is the right choice when you need to ingest and process massive volumes of data, when event sourcing is central to your architecture, or when you're building real-time streaming pipelines. RabbitMQ is the better choice when complex routing is essential, when each individual message must be delivered reliably, or when traditional work queues and priority-based processing fit your use case. In reality, many mature enterprises use a hybrid approach. Kafka handles event streaming and analytics, while RabbitMQ manages command processing and inter-service communication. The right decision is based on specific use case requirements, not trends or hype. Before making the final architectural bet, clearly define your use case. Document your message volumes, latency requirements, and retention needs. Assess your team's skills and operational maturity. And most importantly, start small and scale gradually, learning the system's behavior before committing it to mission-critical workloads. The best messaging platform is not the one that looks best on paper. It's the one your team can operate reliably in production. If you've worked with Kafka, RabbitMQ, or both, share your experience in the comments. Don't forget to subscribe to the Topictrick YouTube channel for more enterprise architecture deep dives that go beyond surface-level comparisons. See you in the next video.